Bismillahirrahmanirrahim. Okay, now let us look on rush time budget. Okay, so why we need a rush time budget? So rush time budget is actually a convenient method to determine the dispersion limitation of an optical fiber link. It is also useful for digital systems. Okay, so let us review on dispersion. Okay, so let's look on fiber dispersion. So fiber dispersion is actually the result in optical pulse broadening. So this optical pulse broadening will degrade or will decrease the digital signal performance. Okay, so let's say this is an optical fiber. Okay, we have the input here and the output is here. And in the beginning, this is our optical pulse. Okay, so when the optical pulse is traveling along this optical fiber, okay, so you can see that the pulse is broadening. Okay, so the pulse broadening will result with digital signal degradation. So basically, there are three main dispersion mechanisms. Okay, the first one is modal dispersion, chromatic dispersion, and the last one is polarization mode dispersion. Okay, so let us refresh back on modal dispersion. Okay, modal dispersion actually occurs because of different modes. Okay, as you can see here, we have different modes. Okay, so different modes or different paths. Okay, the blue lines, the red lines, the green lines, they all have different paths. Okay, so these different paths or different modes will arrive at the receiver with different delays. Okay, because the distance of the path are different. Okay, so that's why they will reach at the receiver at different time. Okay, due to this phenomenon, multimode or modal dispersion or pulse broadening will occur. Okay, so you can see the pulse spreading at the receiver. Okay, so this is what we call it as modal dispersion. Okay, previously we have looked on modal dispersion, which occurs only in multimode fiber. Now, let us see on chromatic dispersion. So basically, chromatic dispersion occurs in all type of fiber, no matter it is a multimode fiber or single mode fiber. Okay, so why chromatic dispersion occurs? It is actually occur because of optical pulse broadening results from the finite spectral line width of optical source and the modulated carrier. Okay, so you can see here, this is actually the spectrum of our source. Okay, so even though we have a narrow line width for laser, but still we have a certain wavelength, okay, at this particular line width. Okay, we have a specific wavelength. So for the case of semiconductor laser, the line width corresponds to only a fraction percentage of the center wavelength lambda naught. But for LED, the line width is likely to be more significant percentage of lambda naught. Okay, of course, for LED, the line width is wider. Okay, so we will have more chromatic dispersion as compared to semiconductor laser. Okay, because for semiconductor laser, we have a narrow line width. Okay. Okay, so let us look in more details for pulse broadening. Okay, pulse broadening limits the fiber bandwidth or the bit rate. Okay, so for example, let's say this is our input pulse. We can see that it is 101 is transmitted. Okay, and then after a certain time, you can see that the pulse is spreading. Okay, and then at longer time, the pulse is more spreading. Okay, and intersymbol interference occur. Okay, so 101 can hardly be determined. And finally, at the receiver, you can see that the signal is already distorted. Okay, so we can hardly read 101 for this signal. Okay, so it is indistinguishable. Okay, so an increasing number of errors may be encountered on the digital optical channel as ISI, intersymbol interference, becomes more pronounced. Okay, now let us look on group velocity dispersion. Okay, group velocity dispersion is actually due to chromatic dispersion. Okay, so we know that different spectral component of a pulse travel at different group velocity. Okay, so these are the different spectral components of a pulse that travel at different group velocity. Okay, so the different component, the red wavelength, the green wavelength, and the blue wavelength will arrive at different time. Okay, so because they arrive at different time, then chromatic dispersion or group velocity dispersion will occur. Okay, so chromatic dispersion can be either a material dispersion or waveguide dispersion. Okay, so let us look on polarization mode dispersion or PMD. So basically, in a single mode optical fiber, the optical signal is carried by linearly polarized fundamental mode, which is LP01. Okay, so this fundamental mode has two polarization components which are orthogonal with each other. Okay, so this fundamental mode has a horizontal mode and also the vertical mode. Okay, so in real fiber, these two orthogonal polarization mode propagates at different group velocity. Okay, this horizontal mode and vertical mode has different velocity. Okay, so because of this, it will result in pulse broadening or polarization mode dispersion. Okay, so we can see clearly here polarization mode dispersion. Okay, so when this input light travels along this fiber, you can see at the receiver, the two orthogonal mode are, reaching the receiver at different time. Okay, so because of this, the polarization mode dispersion occurred. Okay, now let us look on rise time budget calculation. Okay, total rise time actually depends on transmitter rise time, group velocity dispersion, modal dispersion rise time, and also receiver rise time. Okay, so to get the total rise time, we need to square root and then add all the rise time for each contributor, and then we have to square root the value. Okay, so total rise time of a digital link should not exceed 70% for a non-written 0-bit period and 35% of a written 0-bit period. Okay, let us recall back on written 0 bits and also non-written 0 bits. Okay, for written 0 bits, the waveform representation for 1 is like this. Okay, so you can see this is 1, this is also 1, this is also 1. Okay, so for 0, the waveform representation is like this. This is 0, this is 0, this is 0. Okay, for non-written 0, 1 is represented by this waveform. Okay, so this is 1, this is 1, this is also 1, 1, 1. Okay, for 0, the representation is like this. Okay, so just like this. Okay, so this means 0. Okay, okay, now let us look on transmitter and receiver rise time. Okay, so for the receiver rise time, the formula is receiver rise time. This is Rx is receiver. Okay, receiver rise time equal to 350 divided by BRX. Okay, so BRX is actually the receiver 3 dB bandwidth in megahertz. Okay, so if you put here in megahertz, okay, the value in megahertz, you should know that the answer will be in nanosecond. Okay, so receiver rise time results from the photodetector response and the 3 dB electrical bandwidth of the receiver front end. Similarly, for the transmitter rise time, it is equal to 350 divided by BTX. Okay, the unit must be in nanosecond. Okay, so again, BTX is actually the transmitter 3 dB bandwidth. Okay, again, it must be in megahertz. Okay, transmitter rise time is attributable primarily to the light source and its drive circuitry. Okay, now let us look on modal dispersion rise time. So we know that modal dispersion occurs only in multi-mode fiber. Okay, so first you need to determine the BM. Okay, the bandwidth due to modal dispersion. Okay, so let's say BM is bandwidth due to modal dispersion of a link length L. So the formula for BM is equal to B0 divided by L to the power of Q. Okay, L is the link length. Okay, so B0 is bandwidth per kilometer. Okay, megahertz kilometer product. And Q, the value is around 0.5 until 1. Okay, the modal equilibrium factor. Okay, so this value will be given, the Q value. Okay, only then you can find the modal dispersion rise time. Okay, this is the formula, which is equal to 0.44 divided by BM. Okay, the bandwidth. Or you can also rewrite the formula as the modal dispersion rise time equal to 440 times with L to the power of Q divided by B0. Okay, so you will get the answer in nanosecond. Okay, how does actually the modal dispersion restricts the fiber bit rate? Okay, suppose we transmit a signal at low bit rate of 10 megabit per second. So the pulse duration must be 1 divided by 10 mega, okay, 10 to the power of 7, and you will get 100 nanosecond. Okay, so this is the pulse duration. Okay, from above example, each pulse will spread up to 100 nanosecond, approximately pulse duration, for every kilometer. Okay, so for every kilometer, the pulse will spread around 100 nanosecond. Okay, so the broadened pulse overlap and intersymbol interference will occur. Okay, so in this case, modal dispersion limits the bit rate of a fiber link to 10 megabit per second. Okay, so let us see on modal equilibrium factor, which is Q. Okay, the range is between 0.5 to 1. Q equal to 0.5 indicates that a steady state modal equilibrium has been reached. Q equal to 1 indicates a little mode mixing, but a reasonable estimate is Q is equal to 0.7. But in your final exam, the value of Q will be given. Okay, now let us look on group velocity dispersion. Okay, so this is the formula for group velocity dispersion. Okay, so we have the rise time for group velocity dispersion equal to D times L times with the half power spectral width. Okay, so D is the dispersion parameter, nanosecond per kilometer nanometer. Okay, and then we have sigma lambda here, which is the half power spectral width of the source. The unit must be in nanometer, and L, which is the distance, and the unit is in kilometer. Okay, so that is group velocity dispersion. Okay, for single mode fiber cable, okay, for single mode fiber, only group velocity dispersion is considered because for single mode fiber, it does not experience modal dispersion. Okay, so this is the total rise time formula. Okay, so you can see this is the total rise time. It is given by transmitter rise time squared plus receiver rise time squared plus the group velocity dispersion squared plus the modal dispersion squared and the square root of all these values.